So hello everyone. I'm Shashanka, and together with Valentinos, we'll be talking about our new work, Franca, which is towards the open source vision foundation models. Um, so a brief introduction about myself. I'm a researcher at Value AI, where which is a small group of researchers based in Paris, where our main focus lies in multiple research accesses, like you can see, like multi-sensor scene understanding, data annotation, efficient learning, robust and reliable explainable models, all towards the autonomous driving use case, which is part of the more global company value, right? And myself here, I work on the intersection of vision foundation models and also focused on world models for autonomous driving. And together, like with my cohorts or my colleagues at Value, I mean, I just wanted to like briefly mention one of our recent highlights work, which is called VAVIM and VAVAM. So VAVIM is basically like a large-scale video generator model, which is trained on these large-scale raw unlabeled videos, and together from which we kind of now use the representations to predict the trajectories, using imitation learning. So this kind of work bridges the gap between video understanding and also like control and planning. And interestingly, I just wanted to highlight that this was the model that was used for the HugSim challenge in ICCV, where it won the recent award for this. So this is like a very nice recent work of ours. So you can also go and check it out, right? I'll also let Valentinos introduce himself.
And also from me, I'm Valentinos Pariza, and as mentioned before, I'm a first-year PhD student at the Fundamental AI Lab at the University of Technology Nuremberg in Germany. And I'm working actually under Professor Yuki Asano, who is also the head of the Fundamental AI Lab in Nuremberg. And as you can see, this is actually our group on the right, where basically the majority of the people are from the University of Technology Nuremberg, whereas some of them, or the rest of them, majorly from the University of Amsterdam. Next slide. Here, for example, you can see our 4 pillars of research, basically at the Fundamental AI Lab. It includes, for example, self-supervised representation learning, vision language learning, video temporal learning, and large language models. Next slide. And basically here you can see my direction, which is basically self-supervised representation learning for visual understanding. And as mentioned before, it's just for developing new strategies to improve generalizability and stability of vision foundation models. Yeah.
Great. Thanks, Valentinos. To get started, so I think nowadays we are in the world of a large-scale data regime, where we have these, the diverse set of images, taken by different, like millions of people, like usually shared on social media, but you can see a large diversity and variations in these images. And the interesting aspect of these kind of images or these large pool of collection of data is that currently there is no single data set that basically covers these diversities, right? So it becomes very important for models to kind of learn and be able to like generalize on like these multiple diversity of images. So you also want the model to not only just do well on one particular data set corresponding to one particular task, but also you want it to be able to like generalize to, like, let's say object detection, semantic segmentation, depth estimation, and so on, right? And for that we need like one model that is capable of unifying all these multiple different vision tasks, where the goal is to basically pre-train it once and adapt it to like all these downstream tasks. And you want the model to kind of have really good generalizability, or to perform very strong zero-shot segmentation, do perform very well on fine-tuning for different applications like medical data, remote sensing applications, and so on. And this is like one of the goals of the vision foundation models. However, in order to kind of be able to work on these billions of images, scaling them is very important, right? And scaling them involves like multiple different aspects. Like either you kind of scale data, you kind of come up with new interesting loss functions, different model architectures, different optimization strategies, or you kind of just throw in like bunch of compute, right? And most people here are usually worried about lack of compute, especially in the academic setting. And this has been like the backbone or the fundamental aspect of being able to train these large scale foundation models per se, right? And however, one of the so scaling vision foundation models is not easy, right? It's kind of very hard, and the reason is that you see this exponential growth in data, where you have like your new data points coming, new data sets, with different diversities, with different challenges of its own. It usually requires the need to be coupled with these massive compute resources that you have. But at the same time, just throwing a bunch of compute is not the usual solution. It needs to also be efficiently trained, because hardware is usually subject to some kind of training crashes, when you kind of use large node computations. You always have some challenges across syncing batch norms, or stuff, gradients, and things like this. And assuming that all this is solved, you also want to like maintain these generalizations across multiple diverse real world scenarios, by trying to ensure that it's not very costly to compute on a new data set or a new task. So all these reasons coupled with this kind of makes scaling of vision models quite challenging. Right, and in this context, there have been like multiple really great models out there. So I'll just like try to enlighten you guys about the different models. So in case you might have not missed, so segment anything SAM is like a very popular one, which does really well, really good semantic segmentation, object detection, or basically dense tasks on like high resolution data. You have radio from the NVIDIA team, which is reduce all domains into one, and they have had a recent model called Radio V2.5 and C Radio, which is on like the non-commercial data, which is also quite good, where they distill like Clip, Dino, and I think SAM into their student model to kind of ensure it learns like kind of robust representations. And then you have the AIM models from Apple. AIM V1 is it kind of doesn't do the standard Dino style or Clip style losses, but it uses like next token prediction to kind of learn these really good vision encoders. There is a new version of AIM, which is called AIM V2, which uses like it's in a multimodal setting, so it also uses like text generation along with next token prediction for image models. So MV1 and MV2, although is multimodal, not vision, just specific pure vision per se, right? And then of course you have the new like Dino V2 and Dino V3 style of models, along with Web Dino, which kind of now bridges the gap to like not only it performs well on like vision centric tasks, but also like bridges the gap to like more VLM tasks. And I think David and Peter were also part of the Cohere talk a few weeks ago. And then finally, there is perception encoder from the Meta team of Christoph, which kind of also has this ability to kind of generate really good representations by pre-training on large scale like image videos and so on. So they also, and the interesting part is they say that you to get the best performance, you do not have to probe features from the last layer only, and they have really good visualizations of performance gains when you probe like intermediate layers of the model. So all of these are like some recent models that kind of can be categorized as modern day vision foundation models. And here now we present our new work, which is Franca, nested Matryoshka clustering for scalable visual representation learning. This is a collaboration with folks from the Fundamental AI Lab, Value AI, and the Viz Lab from University of Amsterdam. So in order to kind of dive into detail about Franca, we need to first understand, how Dino V2 works, right? Because our model is built on top of Dino V2, and to understand the complexity of Dino V2, so here I'll just go through this in slightly more detail. And this is how the pre-training is done, right? So you have a large corpus of data, and then within each batch you kind of have these multi-crop strategy where you divide a single image into like two global crops with an overlap of, let's say, 60% or so. And then you have these multiple local crops that define like really small regions within the image, right? And then here you have like a distillation approach, where a student teacher distillation approach, where you first kind of maybe I'll just use my pointer here. So you at least like random mask some tokens of the some tokens of from the features of, let's say, the global crops, pass it through the student network, which is a backbone, of course, of it's a vision transformer, let's say base, large, giant, huge now for Dino V3. um, and the thing, it's important to note that both the teacher and the student architectures are the exact same vision transformer backbone, which kind of outputs these set of features. So it kind of outputs patch features or a CLS token, or if you use registers, then you also have registers coupled with it. And then during the pre-training phase, it doesn't just end here. You have like a projection head, and here specifically, they kind of term it as a Dino head and an iBot head, right? So in the Dino head, you pass your CLS tokens, and in an iBot head, you kind of try to reconstruct the masked patch features, from the iBot head with respect to the clean features from the teacher network. And here, the thing how they kind of centered. So in Dino V1, they had this centering and scaling, where they want to kind of ensure that the teacher distribution is more like a Dirac and a target for the student model to kind of learn when applying the simple cross entropy loss. And here they kind of use the Sinkhorn-Knopp clustering, right? And then you apply the standard Dino loss, which is a combination of your cross entropy between the CLS heads, or let's say the features from the Dino head, and the masked patch reconstruction loss from the iBot head. And they have another loss called the Collier loss that uses the CLS token only from the student network. So in hindsight, what I'm trying to say here is that while Dino V2 looks very like easy when you just kind of download the weights from Torch Hub or Hugging Face, pre-training it is kind of very complex because it involves all these architectural changes. It has a lot of details into optimizations, and stuff like that. And while working on Dino V2, specifically taking the code and trying to implement it on our tasks, we found that there are several challenges associated with training this model. So here is a small condensed version of it, but so one of the challenges is that the Sinkhorn-Knopp clustering here is prone to numerical overflow, and this happens like at an intermediate stage of training, and basically your training crashes, and no matter like what you do, you have either you kind of restart from your checkpoint, intermediate checkpoint, previous checkpoint, or you have to restart from scratch. There's always this possibility of, let's say, a numerical overflow that happens because of Sinkhorn-Knopp clustering, and your training crashes. The second thing here, and it's also interesting to note why the Sinkhorn-Knopp clustering crashes or is prone to numerical overflow, is because the features from the output of the iBot and the Dino head is actually projected onto a very large codebook, and this is like a clustering feature of dimension like 131,000 in case of Dino V2, or it's 262K in terms of Dino V3. So the features basically go from a dimension of 384 or 256 to like 131K or to like 262K, which is like super huge. And this kind of causes instability in kind of clustering, because now the feature dimension basically explodes. It's also extremely sensitive to hyperparameters, And the way they kind of set it there is very specific to their data set, and also it's only specific to the large model. So in case now you have to like train it on smaller models, let's say the width smaller, the width base, it's kind of very difficult, because either you have like really poor numbers, or the training loss doesn't converge, or again, like you have this numerical instability, all of this, which kind of affects training. And then you have this very interesting observation, which was made by Valentinos, is that the features have a very high positional bias, right? And which means that the patch features are, because they are trained on these large scale data sets, the patch features basically learn to kind of, understand, or understand objects based on the specific patch location, instead of understanding, features or semantic features from the object itself. And this sometimes gives these really strong performances for Dino models. And finally, if you want to like reproduce Dino V2, it's very difficult, because they have their own proprietary data set, which basically is a collection of almost all academic benchmark data sets like ImageNet 1K, AD20K, Pascal VOC, COCO, and so on, right? And Google Landmarks and so on. So basically, in terms of Dino V2, they have like kind of collected specifically all like downstream data sets that usually people evaluate on, and have trained the model on very specific these data sets. While for Dino V3, they go for Instagram 1 billion, and they start curating a similar distribution of data sets from it's a mix between they do not provide detail, but it's just my understanding that they also curate a lot of academic data sets starting from Instagram 1 billion. So considering all of these challenges, we kind of were like, it's very important for research community to be able to kind of reproduce or understand these vision foundation models, and we kind of work towards the openness of it. So in the first step, kind of very important here is to kind of understand the data itself, right? So here we kind of compare it with works like Metaclip, Web-SSL, Siglib, AMV2, like Dino V2, SAM, and OpenClip. And so works like OpenClip, AMV2, Metaclip, all towards like the multimodal setting and nothing very specific, and Siglib, of course, Clip, and so on, work very specific to the multimodal setting, but there is not a single model that is completely open in the sense of data, code, checkpoints, and so on for vision foundation models. And what we also observed with these foundation models is that although they train on large scale data sets, most of these large scale data sets tend to be very noisy. So it's very important that you kind of filter them out and start like pruning the deduplicates, which is what we term here is like sometimes the dedupe code is not publicly available. We do not know if the data set has been filtered for NSFW or like CSAM and so on. It also becomes very tricky for them for us to kind of even work on these kind of data sets. So considering all these aspects, we work towards the openness of it, like I mentioned, where we tend to use data sets that have all these different properties, where so now we have made our training code public even for the smaller models. There are checkpoints available. Our training data is easily downloadable, even for like a large scale model like Lion Coco, which consists of 600 million images. And of course, we have ensured that it's NSFW safe and CSAM filtered, because Lion Coco is part of Relion 2 billion, which has been NSFW filtered and CSAM filtered. So towards the first step, this was the first step towards the openness of vision foundation models. And now we want to talk about how do we come up with this idea of balancing the spatial distribution of visual patches. What we observed in basically models is nowadays it's very common for these foundation models to kind of use a masked image modeling approach, where they kind of mask certain regions of the image or patches and then try to reconstruct it based on the patch reconstruction loss. Even Siglib V2 kind of does it. And Dino V2 iBot has been very popularly using all of these masking strategies. However, the problem with random or like these block masking approaches is that they kind of lack these spatial structures, and you can see it's fragmented with kind of limited textual like understanding or coherence, right? And in order to solve this, there was another idea called inverse block masking, where they kind of mask a contiguous region of the image, and then they kind of just invert it. Uh, this offers like more like structural context, as you can see from the image, but in most of the cases, the unmasked region is basically towards the center, and this kind of causes some kind of a positional bias again within the model, and which we want to also avoid in our work. And for this reason, we kind of are inspired by copy, which was a recent work by Timothy Darcet, where they kind of introduced this notion of cyclic mask, where you have this inverse block masking strategy, but then you just cyclically shift or like rotate around the image randomly across, and then you do this, uh, you know. Randomly during training, and this kind of ensures a uniform exposure to like all of the patch regions, and this becomes very important for the model to kind of avoid having this positional bias that inverse block masking basically has. And then we wanted to see how this kind of performs as a very initial step, and by just evaluating on like in context learning on the Hummingbird benchmark and doing a linear probing accuracy on ImageNet 1K, we observe that this definitely gives a boost. So from the baseline, what we have, which is the width-based model, cyclic mask basically improves the performance of the model like slightly, right? Although it's not like out there. And then, see, one of the challenges that I mentioned in the Rhino V2 style of training was that it maps the features from a very small dimension to a very large code book of size 131K and so on. So we kind of considered this to be a big problem, because now the clustering is not like semantically meaningful. We do not know what basically the features are being clustered in the Sinkhorn-Knopp clustering. So we were like, is there a way to ensure a more like coarse to fine-grained clustering? And we were inspired by the work from Aditya Kusupati and et al. And group on the Matryoshka representation learning, where we also now introduce this on the backbone of our model. So here, given the encoders, we kind of slice the embeddings. It's just a very simple slicing of embeddings into multiple sub embeddings of dimension d by 2, d by 4, which is like a log scale, until d by 16. And then we kind of so what they basically do is in Matryoshka representation learning is that they map each of these sub embeddings into like a common projection head, and then they kind of train their model jointly, right, with the projection head. And what we realized that was, by doing this, we would basically be blowing up the total number of parameters, because now mapping embeddings from dimension d by 16 to 131K every time would be extremely heavy. And also we noticed that by mapping from dimension d to 131K also doesn't result in good kind of clustering and so on, and results in like noisy artifacts within the features of the model. So it would be very interesting to kind of do this in a sub clustering approach, where the sliced embeddings are mapped to another like nested clustering approach, where each dedicated projection head has a dedicated clustering of its equivalent dimension. And interestingly, what this basically means is that now we capture each of these heads, capture like from global semantics to like more fine-grained understanding of the local structure. And now with this, we kind of are able to jointly train our model. So one thing that would be very obvious to ask is like, now how much is the total number of parameters increased by? And I think for the width-based model, we only increase the total number of parameters by 13%, right? Which is like kind of very minimal, 13. So I think in terms of computational overhead, it's not that much, and we are able to like it does a pretty good job in kind of understand like improving the semantic representations of the model. And now again, like going back, we want to see how each of these components increases or affects the performance. And before that, we wanted to see the PCA visualizations of it, right? So here is in the front row is in the first row is Dino V2, where we kind of slice the dimensions, and then apply a PCA, and with the PCA, and take the first three components, and then and visualize how these components look like. And you can see that from dimension d by 16 onwards, basically the features tend to collapse. While in our case, you can see that even though our model is trained until d by 16, we are still able to keep the semantic parts of the object until as low as d by 128. And this is kind of very interesting, because now we can show that Franca retains like the coherent part structures beyond its 10 dimensions, and we do not have to kind of keep on training until like smaller and smaller dimensions. Training until d by 16 will ensure that you have kept some semantics until like a very small dimension itself. And here is the performance gain. So notably on dense tasks, which is on Pascal work, in terms of in context learning, we see like a huge boost, like around 4% gains in performance. And also interestingly, on linear probing ImageNet 1K, we see like a good 0.6% gain in performance, right? And uh, so this was kind of very interesting, because now the numbers here, especially for dense tasks, show that by doing this nested Matryoshka approach, Matryoshka clustering approach, we are able to like kind of encode these very strong semantic information within the model itself. Another interesting aspect, which we kind of found from DynoV2 specifically, and this is not specific to DynoV2, but it was first introduced in Date 3 from Hugo Toubron and colleagues, which was this concept of high resolution fine tuning. So here, what they do is they kind of pre-train their model on a low resolution input image, which is 224 by 224, and then directly like fine tune their model on a high resolution of size 518 by 518. And what we kind of tried initially, and because the high resolution fine tuning code is not open sourced, we had to like try different like learning rate schedules, different ways, like different number of iterations and so on. And eventually we kind of found that incrementally fine tuning the backbone on 364 and then 518, while also incrementally increasing the local crop resolution, is a very good way to kind of fine tune the backbone. And here we use a data set mix. So our initial pre-training set is Lion 600 million, which is completely of a different distribution as compared to like downstream tasks, which kind of also affects performance, right? But so here, to kind of ensure that we are lying within the same distribution, we kind of perform this high resolution fine tuning on this data set mix, which consists of a total of 1.4 million images, which is very, very small compared to what DynoV2 uses, or even what our pre-training set uses, right? So in this sense, we found that this is the most optimal way to kind of do high resolution fine tuning. And one good thing is that we will also release the code for how do you compute the dataset mix, and then how do you uniformly sample all these into your batch for high resolution fine tuning. And then what we observed interestingly was that on tasks like ImageNet 1K, for example, before high resolution fine tuning, the performance gains were like, we had a drop in performance from like 82% to 81.8%. But post high resolution fine tuning, we found that we have a very slight improvement in performance of 0.6% on classification related tasks. But the major boost in performance came on dense tasks, right? So we went from, let's say, 37.7, this is on AD20K, to around like 40, close to 40%. So which is like a good 2% boost in performance. And on some cases, especially on bit large, for example, we observed like a 6% boost in performance, specifically for because of high resolution fine tuning. So this kind of ensures that, and I think, yeah, this one specifically also shows that from Matryoshka, we get a really good like 3% or 2.5% boost in performance just by doing high resolution fine tuning in an incremental fashion, of course, because I mean, if you do it otherwise, we do not see much improvements there. And this also like improves the linear probing performance, right? I think yeah, Valentinos will now talk about rasa and further steps. So yeah, that's it from my side. I'll just stop sharing.
Yeah, I'll actually start sharing my screen. you see my screen?
Yes.
Great. So we will actually start with RASA, but before actually we go to the details of how RASA works, we will basically kind of say a little bit the motivation of how we actually came up with RASA. More specifically, towards actually exploring the potential of vision transformer foundation models at the beginning on different downstream semantic tasks like the linear segmentation and context learning that Franca showed before, that Franca actually improves, of course, with the high fine-tuning resolution. We actually raised two questions at the beginning regarding that, whether basically the positional information of the image, basically, as we can see here, that is basically encoded by a specific encoder, whether basically the information of the positional embeddings that the vision transformer encodes at the beginning remains actually at the end, basically at the features that we get from the last layer and so on. And basically whether that positional information that is retained, whether it's retained, and whether basically it can affect the downstream tasks like semantic segmentation and context learning and so on, but they don't inherently require positional information, but particularly focus on the semantic information. And basically to do that, what we did was that we conducted a preliminary study to see whether positional information interferes basically with those kind of downstream tasks, and more specifically with whether interferes with the clustering of the features from the vision encoders. More specifically, we are going to show here how we do it, but the main idea is that we take basically a set of images, let's say, for example, an image like this one, then we encode it basically such that every patch basically will be represented by a feature vector, just like here, the first patch, the second, and so on. And we do exactly the same thing for a set of different images, basically, let's say for the whole COCO dataset. And we get basically those features for every image. After that, basically, we cluster every patch vector that we actually encoded from every patch, and we cluster them basically in a set of different clusters. And we cluster them in such a way such that basically every cluster will be basically accumulating or will be aggregating essentially the location from where where each patch came from. For example, here we would actually have a patch in the cluster C1 that came from the image 31 in the dataset, of the row patch location 12, and the column location 1 in that specific image. The same actually goes like that. After that, basically, we map every, basically, let's call it location within each cluster to 1D dimension, so that we discard basically the image location, and then we map basically the 12 times 1 location to its basically 1D dimension. For example, if we assume that we have images of 224 times 224 size, and we assume basically that we use our Dyno-V2 encoder, which has patches of 14 times 14, then we will actually have 16 times 16 patches here in the original image, which based actually on that, to basically convert this basically value to a 1D, it would be basically 1 times 16 plus 9, 25. That's to compute basically its 1D coordinate compared actually to what we have at the beginning. And then basically what we do is that we would actually get, for example, every one of these 1D dimensions within each cluster and compute basically the entropy in such a way such that we will be basically able to see how many positions from each cluster, how many patches from each cluster come from the same location throughout the images. And if, for example, some clusters are the majority of the time coming from a specific location, we could easily assume that that cluster, or basically the cluster creation of that specific one, was biased by the position and not by the semantics. And this is basically what we did as a whole pipeline, which basically creates us a histogram of positional entropies, basically, as you can see here. And here, basically on the right, we can see the patch location entropy from Dyno-V2 and our proposed Fran-ka, which are indicated actually by the blue and green non-overlined plots, basically those ones behind in the background, and the ones actually without the line actually on the top, essentially. And we can also see the entropy that we get from the same models when we attempt actually to remove the positional information, basically from RASA, that we are going to explain in a while. And basically, which RASA basically means the removal of absolute attributes. And basically here we can see at the same time that the results are derived on the Pascal VOC and the COCO images. And we use actually, instead of clustering like k-means, we basically use the prototype head. essentially we assigned each patch feature to the cluster whose prototype is closest in terms of cosine similarity. And on the left basically diagram, we also show the DynaV2 clusters whose majority of patches were coming from semantically from basically the same location, as you can see here. So these are basically some examples that we have found that from this specific cluster and these two specific clusters, we found basically that many basically dissimilar images or dissimilar patches that are semantically not relevant are clustered together, but they're basically kind of all coming from the same location in that specific cluster. In addition to that, what we can see here, that the result of RASA is that basically DynaV2 actually has much less entropy than basically Franca, which basically shows that Franca actually is less positionally biased, or essentially it's more semantically strong than basically DynaV2 features. Similar, basically, RAS actually helps to improve basically the entropy by basically increasing it, and therefore it presumably removes the positional bias, or otherwise it makes basically the semantic information within each feature stronger, such that it could benefit the downstream tasks. Another basically study that we have done is the same as the one before, but in this case, actually, we used k-means, and we did it also with the DynaV3, DynaV2, and Franca. Clustering basically was done with k-means using 65K clusters. And what we can see here is that DynaV3 positional entropy, it's lower basically than DynaV2 and Franca, which means that it's basically more biased, positionally biased than DynaV2 and even Franca. And then we can see that by applying RAS as well, it helps improve the entropy, which essentially helps remove some of the positional information, which could potentially make it more semantically stronger for different downstream tasks. And let's actually now start diving into basically the removal of absolute attributes, positional attributes. As we mentioned before, the goal of RASA is to remove the positional or spatial information from the features of vision foundation transformer models. Assume basically that we have an image. We use our vision transformer here, just like, for example, DynaV2, and we basically encode the different image patches to the embeddings, as we just mentioned before, giving us a feature vector for every patch. For every patch feature vector, we use a dual linear layer to predict its position in the image. We represent the position of an image as a coordinate of a row or column. Therefore, we use two linear layers, one to predict the row and one to predict the column of each position, given actually its feature vectors. And then basically, once we get the predicted patch locations, we compare them with the normalized target position patches that we get from the original position from where the specific patch came from. For example, here they would actually represent the 4 different patches here, which this one would be the row and this one would be the column in the original patch. And we basically make this comparison between our predicted and our target positions via the mean squared error loss, which then basically we use to train our linear layer such that it will be able to predict the position accurately, or the normalized position more specifically. As we mentioned, we only train the linear layer and the encoder is frozen. And this is done basically such that only the linear layer will basically hold all the positional, will learn to predict all the positional information from the specific features. Now, once we train basically the linear layer, as we mentioned before, we have basically 2 different individual linear layers because it's a dual linear predictor. So we have the row predictor and the column predictor. So then given, for example, the patch embedding vector for a specific patch, we can actually use the row predictor to predict the row and the column predictor to predict the column. Now, once the linear layers are adequately trained, these 2 vectors here hold information regarding the row and column spatial information of the vision transformer model. And they are of the same size as the input patch feature vector ZI, that they map to the patch location. Now, because of that, the 2 weight vectors UR and UC can be seen as spanning a plane representing the spatial information that basically can be learned from the specific dataset. Therefore, projecting a patch location vector ZI here, the initial one, onto that plane, which can be done using the Gram-Schmidt orthogonalization, gives us a vector here that projects or represents the positional information of the patch feature vector in that spanned spatial space. Therefore, subtracting this vector from our patch initial vector here gives us a vector that is perpendicular to the spanned spatial space with the positional information, though, removed, while retaining the rest of the information. With this exact way, we can use our learn predictor to remove positional information from our patch location vector. We then try to evaluate whether the features with removed positional information, this one ZI1, can still be used to predict, again, the position of each patch. And they were still able to do it. So that's why we thought of an iterative approach, which can be applied, which basically applies all these steps again on top of the pipeline to train actually an additional dual predictor of layers to minimize the information retained in the feature. So essentially, we repeat the same process for an additional layer. More specifically, imagine that we had the pipeline from before, where we trained our linear layer here to predict the positions of specific visual features, visual patch features. Then once we adequately train this linear layer, we can use it to remove information. So it actually comes here. It's basically being used here after encoding the specific patches here to features. It can be used to remove the positional information using, as we mentioned, as I showed before, the Gram-Schmidt orthogonalization, and then use another new linear layer here to remove, again, the positional information of the already removed positional information from the previous patches. And then basically use that to predict, again, the positions. And then we can do it again until actually we adequately have removed enough, basically, positional information, or we basically can see that there is no more potential of improving or predicting the position from all these kind of removal of positional information iterations. Now, all this kind of RASA that we have seen has actually helped Franca, the base model, to improve slightly in context learning and also in linear probing, but generally it keeps it the same, we can see. But it also has quite also some other benefits. For example, when we compare the different kind of models in terms of semantic coherence, which basically can be done using the PCA visualizations, we can see that generally Franca is very much sharp. So essentially what this metric does is it computes basically PCI across the patches on segment anything 1 billion, and it illustrates actually the first 3 components using RGB color channels. What we observe from the PCA primarily of DynoV3 is that here, for example, there is a positional bias, and it can be seen basically by the bottom right here. Sorry, that is basically, you can see this fluorescent actually color, strong kind of pink color here, which can also be seen here on the bottom left. Here, bottom left again. Wait,
so I just interrupt. Sorry to so on the first row, it's like the top left where you have the pink one.
Yes.
For DynoV3.
Exactly.
For the middle row, it's on the top right, where you can see a pink shade, and it has absolutely nothing to do with the object. And then on the bottom row, it's at the bottom right, where that the pink shade has absolutely nothing to do with any of the objects. So it's a very strong positional bias that we see in DynoV3 PCA features.
Exactly. And this actually shows that even, for example, DynoV3 has been trained quite thoroughly. It still, for example, exhibits some of the positional bias that we have also seen before based on our clustering. But in addition to that, though, Franca shows some comparatively very good results, also DynoV3, in addition to the positional bias, and even actually much more clean than Radio and DynoV2 and DynoV2. The only competitive one is DynoV3, which seems to be a little bit more clear. But still, for example, Franca has been able to be quite competitive qualitatively, we can see. We further actually evaluate our models on the unsupervised object discovery using TokenCat, which segments objects by leveraging patch level feature similarity. On the Pascal VOC 2012, Franca obtains 59.1 and outperforming, for example, the DynoV2, which basically gets 48.3. And also DynoV3, which is basically the underperforming essentially here, both on the VATB as well as on the VAT large. And overall, we can see that Franca is significantly better primarily on the VAT base, but also on the VAT large. Here we can also see on the right the object segmentation Davis 2017, as well as showing again the strong ability of Franca, that basically again it's significantly better than all the other competitive models, even though again we can still DynaV3 underperforming in this specific task. In addition to that, we also basically evaluated our features from Franca and Rasa on different dense tasks, like as mentioned before, linear segmentation. And in context learning, here we can see the results in the Pascal VOC. And we can see basically that different kind of models like DynaV2 and Web-SSL are all basically very close to Franca, but particularly on the linear segmentation, Web-SSL is slightly better. And here, for example, the giant DynaV2 is better. But overall, for example, here we can see Franca being very competitive. But on the other hand, in context learning, which doesn't really train anything, we can see Franca being significantly better even from DynaV2 and Web-SSL as well. And in addition to what we have also seen so far, we also tried probing with Gaussian splatting, which essentially normalized average metrics fit to GS across 6 datasets for 2 probing schemes, essentially the geometry here, and here the geometry and texture. And we used the VAT large backbone to evaluate it. And we measured basically PSNR and SSIM, which basically measure, which essentially means that the higher the value, the better it is. Whereas here, for example, that we measure it in terms of the LPIPS, the lower essentially is better. And again, we can see that at least for the PSNR and the SSIM, Franca outperforms all the other models or the state-of-the-art vision foundation models. Whereas also for the LPIPS, it still actually underperforms for only the geometry, but when we also include the texture, it's slightly worse. But in general, we can see that the Franca, it's very much competitive and even outperforms the majority of the times the other models. So let's actually summarize the main takeaways from Franca. So first, basically what Franca does is that essentially Franca organizes the features, and what it does, and the whole actually process is extremely simple. So instead of just making the model bigger, we cluster features in a nested coarse-to-fine way, and this actually saves memory and compute, but you still get the same or even better accuracy as what other state-of-the-art models get. It's overall, it's an efficient way of getting more representation power without paying the usual heavy cost. So it's actually very much well worth using. The second one, it's one of the lessons from our experiments. It's that the data quality matters more than just simple data quantity. It's not just about throwing more images at the model, but what matters is just choosing high quality, diverse images that apply and also apply good labeling and clustering techniques, as we have seen with Matryoshka. That's what really actually drives performance. And finally, with Rasa, we showed that explicitly separating positional from semantic information, the model isn't biased by where basically something appears in the image. And this actually leads to the features generalizing better, especially to dense tasks. And combined also with the nested representations, this means that the learned features transfer more robustly and across basically different tasks and domains, as we have seen with probing, as well as dense tasks and so on. So overall, Franca isn't just about a bigger, basically, vision model. It's about showing that smarter design, both in terms of how we represent the different kind of data and how we train the different vision encoders, gives us a stronger, more general features without relying only on brute force experimentation of finding the best setup for our vision encoders. Thank you very much. And this is our amazing team that we have worked for this amazing project. Thank you very much.
Thanks, everyone. Like, if you have any questions, yeah, we are happy to answer now.
So let's see. Does anyone have any questions? I don't think there are any questions in the chat. There are no questions in the chat. This is a bit unusual. Yeah. So for me, I would just have one simple question. Would it be possible for us to get access to the slides? Is that okay?
Yeah, I think shouldn't be a problem. Yeah.
Okay. Okay. Thank you very much. Mayank, over to you. Do you have any questions? Any of your flashes of brilliance?
Yeah. Hey, I would like to ask about, like, since you have tried with Gaussian splattering as well as like a different variety of uh, 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 like um downstream tasks. So, like the RASA is kind of hierarchical matrix. Sorry, the Matryoshka representation, which is kind of like is good. But do uh, you guys think about the compute too, since like versus the other Dino V3 or AIM? What's the factor like for the inference part of it?
Inference part is the same
Uh-huh.
basically. So with Matryoshka, we can get like slightly faster boost if you kind of use the sliced embeddings. But
Mm-hmm.
if you want to use the full, so all of this Matryoshka is only done during pre-training, right? And it's done on the projection heads. So during inference, you basically discard the projection heads and just use the backbone.
Mm-hmm.
And specifically, you just use the backbone of the teacher network, right?
Okay.
Uh, so in this sense, yeah, it's basically like you don't have anything extra, but it's just the advantage that you can use now the sliced embeddings as what you saw in the PCA visualization, that even when you go like using much smaller embeddings, you still retain a lot of semantic information, right? So in this sense, it gives you this nice advantage of using smaller feature dimensions, which the other models do not basically give you.
Mm-hmm.
Yeah.
Cool. I had also a question about the Matryoshka head design. So, like,
Okay.
you chose the slice set M D by 2 D by 4 to D by 16, like
Yes.
the per head prototype accounts
Yes.
and temperature. So, did you like test the alternative partitions here too, versus the geometric versus the arithmetic spacing, uh, deeper than going deeper than the D by 16 or the unequal loss weights?
So if I understood your question correctly, you're asking, did I use different loss weights or did I go even deeper, right?
Yeah. So like,
Okay, so
huh.
so the question is, so first I actually tried just using two Matryoshka heads,
Mm-hmm.
and going until 16 actually, improved the performance as compared to just using two heads.
Okay.
Um, that is one observation. So beyond 16, no, because we were also uh, like for a model like with base, where the
Mm-hmm.
feature dimension is just 768, go like dividing it by 32 basically would mean nothing, right? I mean, it basically meant that you have like a very small subspace, and it might not lead to any learning. In fact, it might affect performance. So in this sense, I mean, we tried a very simple experiment but didn't work, so we just left it. We didn't exhaustively push it intuitively because the subspace is already quite small, right? It might make sense to go to use it for like a with giant or like a 7 billion parameter model which has a very large feature dimension. Using with respect to using different loss weights, so this actually was ablated by the original paper, Matryoshka representation learning, and they said that keeping equal weights basically generalizes the performance more as compared to using loss weight. So using different loss weight might work on one downstream task but might not generalize to multiple different tasks. So we just use that study of theirs to kind of show that we are able to just use a single loss weight for everything, which generalizes to multiple downstream tasks.
Hmm. Cool.
And the scaling factor also comes from their ablations again, right? So I
Mm-hmm.
mean, this scaling to the power of 2 basically is an interesting way to kind of
Mm-hmm.
divide and slice embeddings.
Any more question, folks?
I don't think there are any other questions. I don't think there are any other questions. I will say that essentially in this talk we got two papers for one basically. The way I look at it, yeah, we got two papers for one. We got the Rasta and then we got the Matryoshka. So I'm still kind of digesting it to be honest. So as of now, I don't exactly have any questions on my end. No questions on my end. Yeah.
Sounds good. I mean, if you have any more questions, you can always feel free to send us an email, and yeah. So the paper is out. Even the code is publicly available. Checkpoints are out. So yeah, feel free to try it out and let us know if you have any other questions. Yeah.
Cool. Like I had a query that was coming into my head. So like following on the multiple Matryoshka heads. So like does each head kind of in the Matryoshka projector learns a semantically distinct set of clusters, or is it
Yes. So
okay?
so maybe Valentinos, I can share my screen. Just give me a second. Yeah. So yeah, going back to I think the slide. So yeah, I mean they learn like distinct clusters. So instead of having a single instead of having a single clustering dimension of let's say 131K whatever, we also like slice or have we don't slice the clusters. We actually learn different set of clustering per sliced embedding. So
Mhm.
they all learn their own distinct clusters.
Yeah, that's what I thought. Like the other way to do that is to learn redundant information at different granularities. So, like that can, uh, like, uh, uh, my query here would be: could you also provide mutual information or a quantitative analysis to cluster the assignments here to demonstrate like how a hierarchy is meaningful
Yes.
and efficient? Yeah.
Yes, for sure. Yeah, that's a very interesting question. So actually, we tried doing that on more real images using these projection heads, and I think we will try to have this visualization soon. Yeah, that's a very interesting suggestion.
Yeah. Cool. Thanks.
Yeah.
Okay. So thank you very much, Shashank, for being here with us. Thank you very much, Valentinos. Um, I personally still need to do a bit of digesting to really absorb what we've discussed today, but I appreciate you sharing your work with us today. In the absence of any further questions, can you just quickly share with us where we can reach out to you on Discord, on email, wherever?
Yeah, I think our email IDs are already available in the paper.
Okay.
So I mean, you can reach out to us directly via email. That would be great, or LinkedIn as well. Any social media platform like LinkedIn or Twitter. I'm active on Twitter as well, so that works. And also email. I think email is the best way. We usually try to respond.
Okay.